Now with our given reference transfer function, we can calculate exactly the final value and the time. The final value first comes with kW. The unit step response has k as the final value, but I have not a unit step response. I have the step response with amplitude 50 kilometers per hour. So the real step response is nothing else than kW times amplitude. Yeah, kW is the final value of the unit step amplitude. If the input step function has not one but another value, and in our case this is W sub O, then we can calculate the final value of the real step response. And you see with kW1 we get 50 kilometers per hour. And my question now is, think about, is this a good value or bad? Yeah? I can tell you this one means after some time, to discuss next steps of time, after some time the final value is exactly equal to the desired value. A better value than a 1 here is not thinkable, it's not possible, because a 1 here means I want to have 50, I get 50. If this is 60, this will be 60. If this is 20, this will be 20. So that is what I expect from a controller, that the control value reaches after some transition time exactly my desired value. So a better response is not possible. Later in this discussion, we will discuss different types of controllers. We will see that this one is the result of using a PI. The integrator of the controller in the closed loop system makes a 1 here. So anytime if we have an I in a loop, we get a 1 here. So this is a very simple explanation. Later I will do this in more detail. And the next step is that how fast is my closed loop system? How fast is my closed loop system? Very simple. This time constant TW describes the speed. That means how large is TW? Tn is 10 seconds. We know it. K is our 2.5 per kilometer per kilowatt hour. And Kc is 3. So TW is 3. You have a free choice because Kc is free. Kc is nothing else than a gain factor in our operation amplifier circuit. That is a ratio of two resistances, so we can have any value without any problem. So we can select any TW value with my controller. My choice now in this project, my choice is I want to have a TW time from 1 second. That means, here my car without controller starts with constant power, starts moving the speed up to final value with a time constant of 10 seconds. Now I want to have an acceleration. I want to have a fast reaction. I want to have after 1 second 63% of 50 kilometers per hour, after 2 seconds 84, and after 3 seconds 95. So this is my desire, and I want to check, is it realizable? Is it possible? My choice is TW, and with this choice, you see with my knowledge here, I can at once calculate my Kc value. Kc is Tn divided by TW divided by K. So we replace the numbers, 10 seconds divided by 1 second divided by 2.5 kilometers. Kilometer per kilowatt hour. The seconds you see can be eliminated. So finally, Kc is 10 divided by 2.5 is 4 kilowatt per kilometer per hour. This can be, of course, realized. That is just a gain factor of my controller. It could be a digital controller or an analog controller, and the gain factor is not a real problem. The problem comes at another position which we want to discuss in the next minutes. But note what happens with my controller. I could be very fast, reach my desired value in less than, say, 3 seconds. And then I'm driving with constant speed, constant desired speed. So the response is fast. And furthermore, this could be, with a new choice of Kc, could be much faster. So there is theoretically no limit for this speed. Yeah? If I select 1 millisecond, then after 1 millisecond I'm driving 50 kilometers per hour. That is not survivable, of course, but theoretically this is possible. Yeah? So you feel, I think, okay, theory is good, but this has nothing to do with real practice, with real life. Yes, right, if you think in this way, but I will explain and I will show you how we can test reality in the next step. But furthermore, note, PI controller, the final value is exact, time is free. That is the result in a system, in any system. Could be it's in a case, a closed loop system, in any case where your model, the process behaves like a PT1, you select a PI, you apply a pole compensation, set Tn equals process time constant. Then you should know the desired value and controlled value will have after some time same value. And with this K, you can be very, very fast. Now that's the result, the first discussion. But of course, we should check, what happens, and that is the next step. Also, you should do this in the analysis of your closed loop system. What happens with your actuator value? That is, I think, the very important internal step. What you have to do after design: check your actuator values, because this gives real information. Is this realizable? Do we want to have this? Is it a load for your motor? In some controllers, there are controllers possible where this power jumps from negative maximum to positive maximum back and forth, and this is of course not that what we really want to have. But I think the idea is, okay, for this very nice behavior, what power is necessary? Now, next step in the analysis, we are in the analysis chapter, number 3, the third step of controller design. Next step in step 3 is check actuator value. Because the actuator is mostly limited, has a limited power output. There is no actuator available without a limitation. So real life has a limiter here. So you should know, check limitation of power. What we want to investigate now is the step response, the reaction of the power if we do that what we have calculated now. What what happens with the power if we want to do this step. Function for desired value, get this nice response of my car. What happens with the power signal? Yeah. To do this, I make a small redrawing of my plan that you can follow my next step. Redraw of signal block diagram. We have still our reference input. We have still our PI controller with KC and TN. But now I draw the power output in this way and shift the process PT1 in the feedback branch. You see, this looks like this. Don't forget the negative sign. So this is exactly unchanged signal block diagram, but only in the drawing is done in a little different way, so that you can follow me, that I want now to calculate the power reference transfer function. Power reference transfer function. We have now the problem that my power signal gets normally also the letter P for power, and we have complex frequency P. So there could be a mix up of the letters. So I want to change my letter for the power to POW to avoid mixing up. And at this time we have what is here the power? Yeah, that was the power signal. Puff. No, that's better. How can we calculate this? I want to have the response. The output now is my power signal. My input is unchanged, my desired value. And this is a reference transfer function, a new one, the power reference transfer function, we can say. Power reference transfer function. Transfer function containing all information. If this is changed, what happens with what is the response of power? That is what we want to have. So first step is I calculate the power reference transfer function by using now signal block diagram methods. That's the reason why we have done this. This is controller, this is process. And we know, okay, in the numerator we have to write that block from input to output, which is only now FC. And in the denominator we have unchanged values FC times FP. So the denominator is unchanged, but the numerator now is different to my reference transfer function relating to speed. Then here. In this function we have a controller times process in the numerator. And here, different to this, the power reference transfer function has here no process. So if we write this down, fill with the given transfer functions, we see here Kc 1 plus Ptn divided by Ptn divided by 1 plus Kc 1 plus Ptn divided by Ptn multiplied with K1 plus Pt. So in the denominator still we have the reduction, the eliminating of the pole, but here this 0 has no partner in the process, so we have now a different function. And if we simplify this a little bit more, then we can see I have to multiply numerator and denominator now with this PTN to get a good form of the transfer function. Then you see in the numerator we have finally a KC 1 plus PTN, and in the denominator PTN times 1 gives PTN plus, and remember, with this elimination we have just simple a KCK here. KCK. This was the form of the power reference transfer function, and the question is, can we analyze this without going into the Laplace transformation? Idea is, can I find this function in my table, and then of course I can copy the results. For this I have to normalize this function in a way we have discussed just before. Here we have polynomial function with a 1. This is already normalized, but here the first order function has here a KCK. We need here a 1 to have a normalized value, so we have to divide by KCK. KC divided by KCK is 1 over K. Numerator we have 1 plus PTN. Denominator we have here a 1 plus PTN gives PTN divided by KCK, and note this parameter we have already called TW. So far, do we know this type of function? Let's go into the workbook, and if you remember in the chapter before PI, we have discussed the PD and the PDT1, and look here, the PDT1 is exactly a K with 1 plus P times numerator time constant divided by 1 plus P multiplied with denominator time constant. So exactly we have found that the power reference transfer function in our case is a PDT1. Nochmal hübsch. PDT1. See workbook, page 16, row, was war das? Row 12. Row 12. So just make a coefficient comparison and then copy the result. What we want to know is we want to have the power step response. Step response. If we apply a desired step like this, what happens with the power? And the result can be found in this, or in other words, the signal can be directly copied from this curve. This is a step response, a unit step response of my power signal, and you see there is a power peak and then an exponential decrease down to a final value. Exactly that is the behavior of my power signal. So 0 power before we apply the step function, then we have a power peak value. We need, now this is a power signal. Then we have final value. And then we have tangent construction for this curve like this. So we need how large is this time, and then we know, okay, the power final value is like this. So we want to have the peak value, and that is the most interesting thing, is can our motor deliver this peak? We should have a value for the final value, and we should have a value for the time. Then we know all about my power signal, and if this can be realized, if my car can do this job, if my wheels can bring this power on the street. For this, I call this say peak. I call this final value. F times V, final value, and this time constant. I think this time constant is clear. This is already known. If you look into the workbook, note that this time constant here, described in this curve, is the denominator time constant. And the denominator time constant is available as my TW, and this is 1 second. So the part width is very small, the part width is 1 second. So this pulse goes down within, say, 3 seconds down to final value. We need peak value and final value. So I think this is not so trivial, because there's one problem because I need the letter K for my process K, and in my table here this K is also used, but this is a PDT1K. So we have now a coincidence of two names of two different parameters. There are two different parameters. Both parameters use now the same letter K. So we have to be careful to avoid problems. I would propose a table, small table, for the coefficient comparison. Coefficient comparison table. On the one hand, say we have the application, and this is workbook page 60. In my application, for example, I have a 1 over k as the k factor in front of my quotient of two polynomial functions. In workbook page 16, I have the name k. So you see, that is a small problem. What I call here 1 over k is here called k. So we have to be careful. Next is the application denominator time constant is TW. The parameter in the workbook page 16 is called here T1. We have used this already. T1. And the numerator time constant of my application is Tn, and the time constant of the workbook of the numerator is Td. So different names, Td. And furthermore, note that we have a very good parameter in the workbook which can be used for defining, for example, the final value change. The peak value is the step depth, and the step depth is Td over T1. So we can say, okay, step depth is Td over T1. In our case, is the step depth. Then Tn divided by T1, which is 10, because Tn is 10 seconds, T1 is 1 second. TW, sorry, TW. No? Td over T1, Tn over TW, Tn over TW is, in our case, TW is 1 second, Tn is 10 seconds, step depth is 10 in our situation. The application 1 over k is, how large is this? yeah, the application 1 over k in numbers is 1 divided by k was 2.5. Go back to our k. 2.5 kilometer divided by kilowatt hours. 1 divided by 2.5 kilometers divided by kilowatt hour. That is the k factor. Yeah, tw was 1 second, tn was 10 seconds. So that we now can check how large is the final value. Final value is, let's look in my situation here, in my workbook, is the k is the prefactor of my transfer function. The final value is k, that is a unit step response. So our correct final value is k of the prefactor times input amplitude. This was 50 kilometers per hour. So the final value is 1 over k is 1 divided by 2.5 kilometer times the numerator kilowatt hour multiplied with the amplitude 50 kilometers per hour. So if you see this, you see 50 divided by 2.5 is 20, and the unit is kilowatt times hour divided by hour, divided here by kilometer times kilometer, so kilometer per hour goes away. So we have just the power unit kilowatt. So the final value is the car drives with 20 kilowatt after some seconds. If we reach the constant 50 kilometer per hour speed, let's check if this could be. Of course, we have started with our process model response. We have assumed that 40 kilowatt power step ends up in 100 kilometer per hour. So if we reduce this with a factor of 2, also this power has to be reduced with a factor of 2 down to 20 kilowatt. We assume linear systems. Linearity means half the speed gives half the power, or half the power gives half the speed. Yeah, we have just linear behavior. So this is okay. We have calculated this as 20 kilowatt, and this is exactly that what we can expect. Kilowatt. Yes, and finally, yeah, this is known. 1 second. This final value is 20 kilowatt. No, the peak value is nothing else than the final value times step depth. Now you see what happens with my power peak. Yeah, the final value k, peak is k times step depth. So the ratio peak value to final value is my step depth. So we have finally here a peak of 200 kilowatt. And the response to this result of this discussion is very simple. If we set my time constant TW to 1 second, this was my choice here. This leads to a Kc value 4 times physical unit. Then we reach the speed, the final value, within 1 second, 63%, so say within 5% in 3 seconds. This is only realizable if the motor can deliver 200 kilowatt in the peak and goes down with its power to 20 kilowatt, yeah, within say some seconds. This is a response. If 200 kilowatt are not possible, then of course the speed reaction is not possible. Or if you want to have the speed reaction, tell your user, then of course buy a car which has a maximum power of 200 kilowatt. This is, not so easy and not so cheap. So we have a good discussion basic to go to our user and say, okay, if you want to have this, then please buy a car which can do this. That is, I think, a very good method to discuss behaviors with your customer, with your user. So far, I show you in the next video, I show you a simulation of this situation with my simulation program. And in the simulation, I can just make a second calculation. What happens if my motor has only 100 kilowatt or any other value? So in my simulation, I can add nonlinearities. In my theory here, we can only calculate with linear functions, because the theory of nonlinear systems is very, very difficult, and we can do this better in simulation programs.